才看到，是我们的 IG 拎起来了。现在的 algorithm 都是这样的，你朋友看到什么你就看到什么。
推苗费了。
还有其他人到了，来这吗？啊？什么？是啊，好看，是绑定了。
开玩笑啊
！Can someone help explain to a non-Chinese reader? Because I'm gonna explain this example later.
No.
小朋友们等姚一成来，说吵，来，赶紧我们要开始啊！
为什么说到我？
就说你吧，
说我是？
就
又在捧杀我。
Okay. Okay, let's start with this example. Why is this true? This implies what? 一个半小时是3个半小时，你读那半小时是不一样的，对不对？这证明什么 ？Chinese is not associative. It's not associative 吗？承认了，一个半小时什么意思？一个半的小时，3个半小时呢？3个半小时。It's not associative. Language is not associative. Okay, hey, this is. Sorry, I mistake. Okay. 想干一下就可以可能。
那完了。
Sorry, I mistake. So, language is not associative. Later, when we learn free group, we also learn using language and words. Okay. A bit dry. Hello. Okay. All right. So I have hand back your assignment 2. So later, maybe in the last hour, we will discuss assignment 2. At the moment, where did we left? Let's see. Actually, this meme, a lot of memes is very fun one. Actually, there are mathematics inside there, if you can discover. All right, so last time where do we start? We start with coset. Okay. So I mean, because you are young, right? So a very important example of coset is what? In Zn. Okay. So in Zn, a very important coset are what? What are these important coset here? You have 0 bar, union 1 bar, union 2 bar, union so on out to n bar. Okay, and you can see that these coset partition your group. Partition your group, right? Because the intersection is empty. Fair enough. Okay, the intersection is empty. I mean, to be precise, maybe I should put a set here. Right. So if you consider the set containing 0 and 1, they are different. So set containing one element called what? Singleton. Okay, so these are n singleton here. Okay, so there are n singletons. And their intersection is. Everyone follow? Okay, so we see that. So observation. We see that coset partition the group. Okay, coset of a subgroup. Coset always come with a subgroup. So if I say that these are the cosets, so what's the subgroup correspond to? It is a trivial subgroup here. Okay, so this is a trivial subgroup here. Because how do you realize this one? You take 1 times the 0 subgroup here. Okay, the trivial subgroup here. Times here is what? What's the LOC here? It is plus. Okay, so actually we can replace this multiplication by plus here. Okay, and so on. So these are just n times, plus the coset, a trivial subgroup here. Okay, is that okay so far? Okay, so these are the coset. So last time what I say, right? Most, in general, coset are not subgroup. Can you see why general coset are not subgroup or not? In this case here. Can you see why? In general, the coset are not subgroup. Why? You know why coset general is not subgroup? You know? Hey, where's your friend? Yu Xuan. Huh? 在什么？在 A2 都不是来上课，他去什么？哦，去错。谁呀？诶，没出那高湾呢？那首高湾？不懂。哦，他没有来，就你来了咯。
不是我不来。
没有，我想回来会考试题。来，为什么 Y coset in general is not a subgroup? Good. So in general, you don't have your identity. Why? Because identity will live inside your subgroup. Okay, will live inside your subgroup. But we know that the coset will partition the group. So identity can only belong to one of the coset, which is exactly the subgroup. Yeah, only can belong to one of them. Okay. So say that in general, coset are not subgroups. Subgroup. Okay. Because identity element, the identity element can only belong to one of the coset. Okay. Okay, good. So last time we also went through a specific example, right? What kind of subgroup we are interested in? Do you still remember? What is the subgroup that we are interested in? Hey, hello. 听说你走错课室啊？是啊，哦。Okay, so one very interesting subgroup you should always keep in your mind is the kernel of a homomorphism here. Okay, so let's say we prove that this kernel is a subgroup and we can use this subgroup to what? To cut our group here. Okay, we can use this subgroup to cut our group. So we should imagine that the subgroup as a knife. Okay, how does it cut our group? If you start with K and then what? AK, BK, CK, and so on. Okay, it will partition our group. Okay, it will partition our group. And under this homomorphism, what happened? What happened to the element inside this coset here? Okay, so what happened to phi k? What happened to phi ak, phi bk, phi ck? Right. So because it is a homomorphism, pk will get sent to what? Everything in K will get sent to identity. Okay, no matter how many of them there, it will get sent to identity here. How about AK then? AK will get sent to phi phi a. Okay, phi a here. Why? Because if I have phi of AK1, what happened? Get sent to 5A times 5K1, but K1 is in the kernel, we'll get identity. So we just left with CA here. Similarly, you can see that CK gets sent to B by C here. Okay, and then also for BK, we get 5 by B. Okay, right. So this is a very important concept. Later we will do something great with these. But what did you see here? What did you see here? You can see that actually the number of left coset is equal to the number of elements inside the image. So this has to be true for general here. Okay, so I'll put this as a corollary because this is coming from a previous corollary that we proved. So let's get our homomorphism. Okay, and then we will prove that the number of left coset is equal to the cardinality of image of 5. Jialing, do you still remember what the cardinality is? What is it? In the set. Okay, number of elements inside the set. Okay, so we want to show that 2 cardinality is the same, right? Okay, so what should we do here? Okay, so since this is a corollary, so let's apply this subgroup kernel phi to our counting formula. Anyone still remember what our counting formula is for subgroup? I recall 浩辰、洪瑞还是浩辰？浩辰有浩辰这个人吗？还是浩瑞？浩瑞啊，浩瑞 has okay. So counting formula is what? Can you recall for us? Forget. Okay, go check. Check the note. Then next one. Yeah, I think related. About home rate. Can you recall counting formula for us? There was. What do we call it? Good. So wait, let me recall this. So the cardinality of G is equal to the cardinality of H times the index of H in G. Okay, so what's the index of H in G? The number of left coset. Remember the diagram I draw or not? If you remember, if you cannot remember all these words, you must remember the diagram I draw. Okay, what's the diagram I draw? I use this subgroup H to partition my group. But we prove that, what did we prove? We prove that all, where did we prove it? We prove that all left coset have the same order, same cardinality. Okay, so once we partition our group, okay, all the coset will have the same number of elements here. Does it make sense? Okay, so that's why we have number of coset times the order of subgroup is equal to the total number of G. Remember? For example, how we get 16 here? Total number is 16, right? We use 4 times 4. Okay, where does the 2, 4 come from? One is coming from the cardinality of H. The other is coming from the number of left coset. Okay. So if you cannot remember word, you have to remember picture first. And then speak from the picture. Okay, speak from the picture. Okay, right. So since kernel of P is a subgroup, right? Kernel of 5. So what do we do here? So we know that cardinality of G is equals to the cardinality of curve 5 times the index of curve 5. Okay. Okay, so this is what we know. Okay, so like what I said last time, right? You want to show that two number is the same. Okay, what are the two numbers here? One set is set of left coset. The other set of images. Okay, so you need to build a bijection between the two sets. Okay, so let's define bijection psi. Okay, psi going from where to where? Psi going from see how we draw this set of all the left coset. Okay, do we know what's K already? So let's denote it. Let's denote it. So let A be the kernel phi. Okay, such that A is in J. And then with what? With image of how to build this map. Last time I told you, right? If you see two spaces, write down one obvious map first and then see if it works or not. Okay, what's the obvious thing to do here? What's the element inside left coset? Set of left coset. What are the elements here? AK, some AK, okay, some AK. But where you gonna send this AK to? Maybe you can do by A here. Okay. Does it make sense? Okay, and then we check. We need to check what? Okay, it's not just define that it works. Okay, we need to check whether it works or not. All right. Right. I think when we define this, there's some ambiguity here. Okay. Whenever you define, you need to first check that whether phi is well defined or not. Okay, so what does it mean by well defined? Meaning it really define a function or not. Okay, how to not be a function? How to not be a function? Many to one is not injective, right? Injective, okay, or not injective only. The problem is one to many. Okay, so what you want to show is the other direction of injective. Suppose AK equals to BK for, let's say, A not equals to B in G. We want to show that BA is equals to AB. Okay, phi A equals to phi B. So this is the other direction of injective. Because to be injective, you show what? Suppose the image is the same, they have to come from the same one, pre-image. Okay. So this is to show it is well defined. So let's show it first, and then I will tell you why we need to do this. So how to do this? Are they the same or not? Why are they the same? Let you think a minute. See if you know how to show. Maybe one hint to give you is the TFAE that I proved to you last time. There's one TFAE I proved to you last time. Think about it. Why is it true? Okay. Okay, can you recall the TFAE statement there? What do you know if two left coset is the same? If the two left coset is the same, implies what? By the TFAE proposition last time. What do we know? If the left coset is the same, implies what? 有吗？全部人有在看吗？回去看啊，我给你 hint，你就代表要去看这个 hint 啊。What do you have? A inverse B is what? Live inside the kernel of phi. But this implies what? Phi of A inverse B is what? Identity. But phi is a homomorphism. It will send inverses to inverses. So we get that by cancellation law, dB equals to B. Okay or not? Okay. So, you might wonder, 哎呀，反正都是一样的东西，那也可能会送去不一样的地方。then 你这样想就有点错了。为什么 ？Why For example, in the case of Zn, how many ways to write one bar? Can also write it as m plus 1 bar. But if you write in these two ways, what happened to this map? What does this map tells you? First, you need to send to phi 1. Second, you need to send to phi n plus 1. So there's no guarantee why these two has to be the same. There's no guarantee. Does it make sense or not? Because your phi already had on different thing already. There's no guarantee. Okay, so you need to check. Actually, it does send to the same place. Okay or not? So because of our equivalence classes, okay, we need to consider different representative. When we define maps, we define on representative here, okay? But what we're gonna send here is an equivalent class here. Okay, so we need to check whether the map is well defined or not. Does it make sense? Okay. Okay. So whenever you define something, you need to ask yourself whether the function is well defined or not. Make sure you're only saying same thing to a unique thing. Because in our group, sometimes we will consider equivalent classes, map from equivalent classes. So if you pick different representative, your function is defined on representative, the exact A. Okay, if it is 1 bar, I'm going to send to P1. If it is n plus 1 bar, I'm going to send to phi n plus 1. But on the world of domain, they are the same equivalent class. So the question is, do they get sent to the same place or not? If they do, then your function is well defined. If they don't, then your function is not well defined. Okay or not? Does it make sense? Yeah. Okay. Question? Any question? 有question 了 ？question， 嘉玲，明白吗？明白。哎，我班上啊没有表现分啊，不用表现给我看 ，OK？ 你同学讲优异系有表现分，我班上没有表现分，我要知道你会还是不会吧？不会你就讲不会吧。start 在一个怪怪的地方也没有问题啊，因为你同学可能也 start 在那里。真的真的真的。Okay, so make sure you point out where you stuck. Even a very stupid one. Okay, right. So after checking well defined, then we need to do bijection. Okay, so we need to prove the bijection. So to prove this bijection, we will use surjective and onto. Sorry, what am I saying? Surjective and injective. Okay. So one of them is easier. You sure? Why is it? Surjective is easier. Correct or not? What do you need to show for surjective? Given any y in image of 5, what do you need to do? Want to show that there exists some x in the set of left coset such that the psi on x will get sent to 1. Who do you pick? What x can you pick? Am I just writing the right thing? Yeah. Huh? Roman? A bit confused. So when is phi, when is phi? So let me bring this mapping down. So let's bring this down to remind everyone. Yeah, our definition of map.
Definition is AK, not AH.
The
definition is AK.
Oh, okay, thank you. So we change the subgroup. So let's keep this. How about we just change the color here? So remind us here. All right. So how to find x? So if you are using this map, how do you go backward? You need to know how to write your element in phi A first. Okay. And then how do you pick? You just put A beside K. But here is Y. Doesn't look something like this. Can you make it look like this? Sorry? How do you make it look like phi of something? Where's Y from? Y is from the image of phi. But image of phi means what? How do you live in the Mars? Last time I asked you, right? You must come from the moon. Sorry, come from the earth. So there's someone that gets sent to you. Okay, so by definition, or by assumption, there exists a, let's say, B in where? In G, such that phi B equals to Y. Or maybe the other way around, you feel more comfortable. I'll write like this. Y equals to phi B. Okay or not? Don't confuse. We have two maps here. Where's phi going from? Phi is going from where to where? So let us talk here. Phi is going from G to G prime. Okay. Okay, so in this case here, is it clearer how to pick our x? What x should we pick? What x should we pick? What x should we pick? So imagine this one, this guy is in here already. So what x should we pick? So here is phi b. So what thing we should pick here?
sorry, B, BK. So we choose X equals to BK such that if I do psi on BK under the map, I send it to where? 5 or E. Okay or not? Hey, do you guys know how to read this notation? This notation, is everyone okay or not? This notation means what? I send the domain elements to a codomain element. But if you write it as function, how do you show it? This is exactly what? PA is exactly defined by psi of A, K. Okay, let me write it smaller a bit. This is defined by psi of A, K. Okay?
So psi it AK give you phi A. Okay, so here is the same. Psi it BK give you phi B. Okay? Is it clear? Question? Give you 30 seconds. Any question? Question? Suppose not to confuse, if you confuse, you must ask. Any question? Okay, follow. 什么？看我，不要看他。看我。有问题吗？没问题。没问题。OK。啊，直接收效。没问题。OK。
All right. How about injective? What's the definition of injective? It's the converse of well-defined. Okay, so we want to show that psi is injective. So suppose what? Suppose psi of AK equals to psi of BK. What do we want to show? We want to show that AK equals to BK. Okay, but by definition, what is psi AK equals to psi BK? It is just phi of A equals to phi of B. Okay, again what? This is the TFAE statement, one of the TFAE statement. So if you don't want to use this statement, you can just play around with your homo. And then you see that A is in, I think, okay, I mean, I think we don't want to go through the proof, right? So because a bit tedious, we need to go through the K first. So by the TFAE proposition, we get that AK equals to BK. Okay, it's the same proof. Because why? Last time we proved that the statement is TFAE equivalent. So you can go from here, phi A equals to phi B to AK equals to BK, and then from AK equals to BK to phi A equals to phi B. So in this case here, one direction proves that psi is injective. The other direction will prove that psi is well defined. Okay, so you use both directions here to show different things. Okay. Okay. Any question? Question? 一凡，明白吗？有问题尽量问啊，这样问。对。陈 B， where's 陈 B 啊？陈 B here or not? Any question or not? No? Okay, feel free to ask. Don't be shy. 不要害羞啊！几岁了啊？你们？2岁。这边是19还是20啊？这个班还是21、19、20、18、19啊？Mostly 19、20。OK。 可以了，够大了，成年了，老了。Adrian 讲的，不是我讲的。Okay, okay, good. Let's continue. So again, more corollary here. So let's deal with only finite groups. Finite group. 会咩？这样讲咩？怎么人家都讲我很年轻啊？没有，那是真老，不是越来越老。Okay, so let's see. So what have we done? Actually, what we have proven is we split our G into kernel of 5 times image of 5. So meaning what? You can compute the number of elements inside a group using what? A homomorphism. Okay, if you know the size of the kernel and if you know the size of the image, then you can compute the size of your group. Obviously, here our G prime is also finite. Okay, so that both sides is finite. Infinite 不懂讲算哦，不会除哦。Okay, 只有 finite 吧。So in this case, what can you see? You can see that kernel of phi actually divides the size of J. Okay, 宇轩，对吗？如果有 A， 是不是有 B？ 现在有没有？啊，搞清楚了吗？什么号码除什么？有了 A 是不是有 B？Example 4等于2乘2， 2是不是可以除掉4？ Okay. Yeah. Divisibility is one of the important definition you need to know. Okay. One of the definition you need to know in this class here. Because like Adrian say, your size of the subgroup determine what kind of subgroup you could have inside your group. You still remember? If you want to be a subgroup of the group, what happens? The order of the subgroup must divide the order of your group. Actually, it's quite restrictive, don't you think so? Let's say your group has order 100. What kind of subgroup you can have? 1, 2, what else? 5, 4, 5, and then I think there's some more before 25, right? 20, 25, 10, yeah, 10 first, 20, 25, and then 50, 100. So these are all the factors of 100. Quite restrictive, quite restrictive. Okay, there's a condition on your size. Okay. Then what else? The last one is the image of 5 will divide both G and G prime. Okay, the size of image of 5 will divide both the cardinality of G and G prime. You agree or not? Why divide G prime G? Because of what? Why divide? Because of why the cardinality of image of 5 will divide the cardinality of G? By part A. By part A. Second part, why also divide the order of G prime? Where does image of 5 come from? Or where it lives? Image of 5 live in where? G prime, right? So, how to divide? Image of 5 is a subgroup of G prime. Okay? So, order of subgroup must divide the order of the group. Okay, okay, so I left at the exercise, write all the proof down for this question here. So, Try write yourself, I already tell you the answer. So let's take an example. For example, what? For example, Sn. So Sn has a homomorphism that you study, right? Which is the sign homomorphism. Okay, sign do what? Send the even permutation to +1 and send the odd permutation to -1. Okay. So what's the kernel here? Kernel are all the even permutation. But there's a name for it, right? These are the alternating group. Okay, so these are the alternating group. So let's say I ask you a question. Hey, I know Sn how big already. Sn how big? This is your high school problem, right? How to permute n elements. Wanji, you have an n tong. Want to put n object, right? And an n placeholder. Okay, you want to place n object. How many ways? N times n minus 1 times n minus 2 times n minus 3. So this is the n factorial. But if I ask you a question, hey, how big is an? Okay, I give you a thing, 1 minute. How to find the cardinality of an? Using what you know? Right? Try and think. I think there's really only one formula is useful here, right? Which tell you the exact number of kernels of homomorphism, which is Rn. Okay, so I try work from there. Do you know what's the cardinality of image? Do you know how big is G? Okay, anyone got any answer or not? What do you get? Huh? So G here is Sn. 来子轩 what's the numerator? What's the denominator here? Numerator is what? Size of Sn. Huh? Size of Sn is what? N factorial. Size of image? How many things inside this image? 2 things only. Okay, so divide by 2. So your An, how big is it? Half of your Sn. Okay, half of your Sn. Go and test it out. Go back, take your S4. S4, how many elements inside there? 4 factorial. What's the number? 24. Half of it is what? 12. So can you find a subgroup of order 12 or not inside there? Okay, just with even permutation. Try it. Okay, and then what is A3? A3 got how many things there? S3 got 6, right? So A3 got how many? 3. So what's the alternating group for S3? Find it. Okay. Are they all even permutation inside there or not? Write it down. Okay, these are very important example for your assignment. Okay, write it down. X1, X2, S3, X4. At least do until S4. S5 is quite large already. 120. So there are 60 of them. That one I don't require to do, require you to do. Okay. At least do to S4. Okay, it will be a very good counterexample in future. Next, let's do this proposition and then we will take a break from here. So next is about the multiplicative property, okay, of index. So what do I mean by this? So meaning there are 2 things want to get multiplied together. So let's get ourselves 3 subgroup. Okay, so we have G with a subgroup H and then with a subgroup K. Okay. We don't require it to be proper, it's fine. But what? So there's something about index. So how many index you can form here? You can form index using H. You can form index using K with respect to G. But there's a third index you can form here. Because K is a subgroup of H. Okay, so I mean, let's make it clear. So let's do it like this. K is a subgroup of H. So you have three of them. Then you will see that the index of K in J is equals to the index of H in J times the index of K in H. Okay, so spend a minute. Try and draw these three pictures out. Okay, try and draw this picture out. See why it works. Try and draw. 画一下在你的纸上或者你的 iPad 上，超声来画一下，画一下这三张图为什么是对的？画一下，画在你的纸上，画一下。Okay, first you use K to cut your G. Second, you use H to cut your G, and then you use K to cut your H. 画一下，为什么是对的？Try and draw. You must draw. In this class, you better draw. Otherwise, you're lost in the jungle of algebra. Okay. So how do you draw it? So on one side, you should have your G. On the other side, you also have your G. So on the right-hand side, right, you can cut your G with your H first. Maybe something like this. Okay, so you, for example, you have H, AH, BH, and CH. But you're gonna cut your H with your K. Okay, but you're gonna cut your H with your K. So for example, this piece here, let's cut into two of them. Okay. But what does this picture want to, this equation want to tell you? It turns out that if you cut your G with your K, okay, let's say I got so many K here, AK, BK, CK, PK, K. GK. Okay, then similarly, you also can cut all these into, say, PK, QK, RK, XK, TK, and maybe WK. Okay, so no matter in what order you cut, they should cut to the same number of pieces. This is what this question says. Can you think of how to prove it? How do you prove this thing? Sorry? Draw it. How to draw? We already draw something like this, but not precise. Okay. So one easy way to see is you should see from the formula, right? What's the counting formula? So there are three counting formula related to these three index, right? What is it? So let's list down here. So what are the counting formula you have? How to use this three index here? the order of G is equals to order of K times index of K in G, and then order of G is equals to order of H times index of H, and then order of H is equals to order of K times the index of K. So I mean, like what you say, right? You are lucky. People already tell you the statement. So start from the statement. Work backward. Can you see why the backward is true? What do you get? G over K equals to what? G over H times H over K. Is it true or not? True? Is it true? True or not? Is this true or not? Okay. But this is only true when H is finite. Only you can do the cancellation. Or the K is finite. Okay. So this should suggest this statement. Okay, and then you can try and prove it in more general. Okay, maybe one of them is infinite. Okay or not? Does it make sense? Okay. If everything is finite, then this works. Yeah. So let's provide one more proof. Okay, let's provide one more proof. So we'll write down all the definition. And then this proof, okay, although we assume that the index of H in G is finite, and K, the index of K in H is finite, but we claim that the following argument that we are going to go through will be or can be generalized to one of them or both of them is infinite. Okay, or one or the other. Okay, let's go through the statement first, and then I'll leave the infinity case to you. So, how do we do? What's our goal here? Maybe we forget our goal. If we assume that the index of H is M, index of K is N, we want to show that the index of K in G is M times N. Oh, this is what we want to show. Okay, this is what we want to show. Right. So what do we do first? Like what I told you, right? Algebraic proof. What do you do? Spell out what you have. Just spell it out. Just spell it out. What does it mean by the left index? Sorry, the index of H is M. Index of K in H is M. So what does it mean? Okay, so we spell it out one by one. By assumption, what do we have? We can list down M coset. Okay, we can list down M coset of H in G. Okay, how to list? We can pick some representative. Okay, for example, what? So say we have G1H, G2H, all the way up to GMH. Correct or not? Okay, we cut into M pieces. Hey, come on. 什么问题？什么问题？可以回去一点。什么问题？啊，没有，可以回去一点。什么问题？我看到你摇头。什么问题？还是要画图？所以我有 G， 然后我有我的 H 是我的刀嘛，对不对 ？G 我有一把刀，我要切成几份？切成 M 份。So there's M of them here. So G1H, G2H, dot, 一直到 GMH. OK 吗 ？OK， 对呀。OK. All right. So, but what does this mean? If I got all of these, what does it mean? we say that these coset will partition my G. Okay, so not that. What is my G? My G is the disjoint union of these coset. Okay, M of them. Okay, disjoint union. Again, play the same game. We have another index, right? Okay, play the same game to the subgroup of K in H. So similarly, we can write H as the disjoint union of Hi K for some Hi in H. Okay or not? Okay, so how do we put these together? So here is the magical statement now. This is the magical one. This requires you to think a bit. Okay, so the magical statement here is now, what is GIH? I know how to partition my H. I know how to partition my H. So GIH can be further partitioned into GIH. Sorry, shouldn't use the same I. Maybe use IJK. Okay, of this. Okay, if you feel uneasy what I'm doing, let me spell it out for you. We have GI H1K union GI H2K union GI H3K and so on. Okay, all the way up to GI HNK. Right, so how we get this HIK? This is from how we partition our H. Okay, and so. Okay, so the claim is this is a partition of the coset GIH. Okay, so this is the partition. Okay, if you want to ask why is it true, suppose it is not, then we will have a contradiction to this guy. Okay, if it is not, then there's a contradiction to the partition of H. In this case, what? In this case, we can write all of them together, right? So what is a G? G is all of these. So G is the disjoint union of I from 1 to M of GIH, but we can further decompose H using what? Using the disjoint union of HJ. Okay. So can you see that we have product of coset? You see that we have product of coset now, 对吗？这是乘法吗？每一个都有 n 个，现在我有 m 个东西有 n 个，所以总共加起来是不是 m 乘 n 个？当然了。Okay, so for one of the GIH, I partition into n part, but I have m of GI. So each of these m of GI has n of GIHK. Okay, so m times n total. Question? Question or not? So, yeah, so getting partition into M n coset of GI HJ K. Question? I will. Yes. I mean this part here. Yeah. Because I can decompose H first, and then I multiply GI to all these partition. I can decompose. So what's this? This is simply GI times the element in the set. But I can first decompose this set. So let's draw it. So this, if you draw a picture, this is GI multiply a set H. Okay, so multiply every element inside here. But what do? You first partition first, and then you multiply. It's the same thing, right? Yeah, it's the same thing. Yeah. So maybe one how to say, one worry you have is, hey, how if I know if I multiply this GI here, it doesn't stay here, maybe it jump to the other partition. You get what I mean? Maybe when you multiply these two, let's say, for example, if you multiply here H1, here H2, in case maybe GIH1 equal GIH2 appear in different partition, then the intersection is not empty. And my claim is it won't happen. If it happens, you will have contradiction to partition H. You can try it out. Then go back and try it. Any question? Question? So that means this GI won't affect this partition one. Maybe it commutes partition, but you won't have an intersection. Okay, go back, test it out. Try and prove. Okay, suppose there's a non-empty intersection between the two. You get contradiction. Okay, suppose there's a non-empty intersection between these two. Okay. Question? Any? One more, maybe one more, then we take a break. Hey, man, Jimin. The back. Any question? Hey, by the way, have I advertised my talk tomorrow here? You know I'm going to give a talk tomorrow. No? Hey, are you guys stay in the teams or not? The mathematics teams. Are you guys in the team? Are you guys in this group or not? I'm curious actually. Yeah, department. Where is it? How to go there? Team, and then are you guys in this one? All of you in here. So we will announce seminar here. Okay, so tomorrow is my talk. It's a joint seminar with Xiamen, China. Okay, so we will have a joint call there. So it's tomorrow 3:30 to 4:30, A4G04. So if you are interested to see how pure maths research is done, you can come and see and watch, and then see how I counter people. Because some people may be a bit tricky. If you are interested in my research, also you can come. Maybe you want to do FYP with me, you can come and listen first. I mean, maybe most of the content you won't get it, but I think you will get more than what calculus students do. My calculus 2 student. Mostly I will deal with group. Actually, that's exactly what you learn now. But it's a specific group, which is a break group. Actually, there's a close relation between break group and your symmetry group. Yeah. Then the line that I asked you to draw in class 1. Yeah, those things. Okay, if you are interested, you can come tomorrow. All right, so let's take a break until 6:16.
那个切蛋糕的图，切蛋糕。你不觉得 A 肯定是要在 AH 里面的吗？
A 要在
然后你把这个 A 扔到 H 里面去吗？
等下给我3次。
这个需要想吗？
我等一下，我觉得要今年，我也是，因为我看到我以前画的时候，我确实也觉得有问题，然后赶紧把其他的乱画进。确实。
我问你啊，你在做你的 notes 的时候，是不是很多画都是去年？
对呀。然后我加东西或者我改，
就是懒，
我叫就是懒，就是一样的东西啊，
就是懒。
就一样东西，
好吧，
就一样东西
那你应该重新写一遍。
啊，不可能，我重新写一遍也是一样。
你上
没有我就改罢了
你。上课的时候也重新写一遍，为什么你不直接拿你上课的东西改？
上课是要现场写吗？不一样那个。
好，
对呀，I mean 没有，我是拿去年的然后改。
哦，
我才发现去年的东西有些有问题，然后就要改了。那你那些看到有些我改漏了，就被你看到了。
确实。
对啊，还有包括这个 label
没人帮你改，非要让今年来。
是去年他们就，哎，一言难尽，不要再说，
对啊。
一言难尽，不要再说。
完了，
哦，我在说那个 AK 应该不在于去年，AK 肯定是要在于去年，所以我在跟他说图画。
最开始你说，哦，对，没有错，对，没有错，谢谢，自然解语。Okay, I will call out names now, and then you can let me know whether you did your assignment one feedback and your assignment two. I just give you back, right? So tell me whether you have put your name already or not. If you haven't, have you submitted the version that with your name? Okay. So if I call you, you let me know. Have you done it? How young? Okay. Have you done your assignment one feedback? Assignment two, eh? I just give you back. You can try and write your name and then send it back again. Okay. Hongjie, have you put your name down? Yeah, assignment one and two. Ziming. Okay, Ziming, did you put your name? Haven't. Okay, on the way. Okay. Zihang. Tân Zihang. Tân Zihang. Yeah. Adrian. Yeah. Gia Ling. Gia Ling, eh? Han Gia Ling. Gia Ling, have you put your name down? 第二个 OK， 第二个也弄一下。子轩有发明，说这啊 OK 好。Lydia 忘记你有没有发明？一和二都有，一和二都加了。OK， 没有在看，等一下再叫看。道奇，两个加了 OK。Eugene 有加吗？一罢了 OK， 二也做一下。Jasmine, did you put your name down on your assignment? Both got that. Okay, then that's fine. Albert, you haven't, right? Can you do for both? Do it now or can you do it now? Or when you go back? Not bad, huh? So you download both feedback file and then put your name and submit again. Submit to the new link. New link再来 put on. 陈 B 还没有回去加哈，1和2还是加了一个啊？2还没加。OK。金鱼 ，Yeah， 金鱼 ，Have you put your name in your assignment？ 两个都要啊，1和2 feedback file 啊。浩瑞 ，OK， 有吗？你交了吗？加了，两个都加了。OK， 哎，喂，不是，你是后来改吗？你后来改是不是？你改一下，因为我没有用那个后来的版本，我是用第一个版本。Yeah， 因为之前的 submission 就不要移动它，不要改动它。子豪哎，子豪有在吗？曾子豪，曾子豪，曾子豪，加黄嘉玲，名字放了吗？现在放了 ，OK， 两个都要。戴一层，戴一层呢 ？OK， 放了吗？名字还没有，两个都要放 ，OK。feedback file 啊，我有写的那一份。心仪，心仪和心仪还没交，几时交？晚上啊，记得啊 ，OK。修童呢？等修童在吗？你1和2都还没交，一交了，2还没啊？2可以交了，我已经派回去了。冰夏呢？冰夏名字写了吗？1和2都要啊，feedback download 下来，写上名字，交上。心灵几时做？回去做，现在啊，现在做了比较好，回去不用再想了。小月呢？小月有写名字吗？上面你有写吗？Sorry，哎，中文名不可以啊，要英文名啊，因为你的正式文件是英文名。好好，哎呀，正式文件用英文。刘子涵呢？现在交啊，好。黄瑞交了吗？哎，你本来就有名字是不是？哎，黄瑞你平时有做课本练习吗？挑着做一点呢。啊，有没有做那种 extra 的？没有，有时间做吗？可以有，那就有呗。要鞭策一下，OK，鞭策一下才可以进步。I mean，你能够努力的时间啊，其实就剩现在吧。比如说，你看我现在出来做工啊，很难再读书了，其实很难再读书，真的没有像以前那样全时间读书，就是你有很多顾虑啊，生活啊，你的家人啊，对不对？哎，黄瑞，如果你能够做的话，你跟那个康平一起做，这样效果比较快一点。啊，呀，如果能的话，宇轩，宇轩加了吗？名字写了吗？写了，两份都有。哎，你本来是有还是没有啊？OK，加上去啊。好，两份哦。孙佳怡，来，佳怡加了吗？正在交啊。OK，两份都要啊。王芳瑜，名字写了吗？OK，王佳怡呀，加了，两份都有啊。苏瑶，苏瑶都加了，谢谢。林夕呢？有交吗？原本就有啊。OK，好，谢谢。常云，来，常云还没交，两份都要哦，assignment 1和2的 feedback。哎，你本来就名字了不是？你检查看，你检查看，我忘记了，没有啊？这样名字要加上去，名字和 student ID 啊，两个。颜色呢？都交了，OK，交一层，对，还没交，交啊。颜色平时有空吗？有空，很有空是不是？ 你也跟康平很好，不是？一起做了，一起做，一起做。OK。高冷，哎，康平怎么也这样高冷？OK，一凡还没加啊，2份都还没，2份还没加啊，记得加啊！啊，钟一凡，来加了吗？马上加啊！康平，康平记得写名字，康平加了吗？对 r o s i n 加了，赵胜，赵胜有写名字啊，好像你本来就有不是？你本来就有 Manchun， 当然啊 OK， 昊天，昊天 OK， 昊天狗本来就有名字不是你们？金星呢？有吗？加了啊。一航呢？一航不在，一航不在。就这加了2份啊。Rachel, you already have got your name right? You type out right? Remember? Okay, good. 韩星，韩星有名字吗？好像没有吧？哦，加了 OK。林恩加了 OK。Ian, where's Ian? Have you put in your name? OK。郑月 OK。张瑞没有在你再跟他讲，你跟他讲。金鹏呀，加了吗？现在加2份啊。伟哲人没有在啊。林晶有你名字也是没有，能发交一下吗？交了2份啊。Okay, so let me see we got a target to hit today we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have this last 8 slide to finish, and then our midterm will reach until this 8 slide. Okay, and then we got time there. We discuss our assignment. Okay, this is the last 8 slide for your midterm. Okay, until today. So we must hit this target before we go home. Okay. Right. So all these while I just talk about left coset here. Similarly, you can define right coset. You know how to define right coset or not? Instead of multiply on the left, you multiply on the right. Okay, so you can consider the right coset of a subgroup of a group. G are the set. What's the set here? Hash A. Okay, instead of AH. So I want to exhibit one example for you. So let's take a simple one. Just take a subgroup of order 2 inside S3. Okay, so now I want you to take out your pencil. Okay, work it out. Let's work together. What are the left coset and what are the right coset? 来，笔拿出来写一下。So list down all the left and right coset. 最多只有6个东西给你乘吧，而且有一个很简单，就是 identity， 其他的乘一乘。So list down all the left and right. 看一下发生什么事情。来，我给你3分钟，我们等一下一起检查答案。Give you 3 minutes. List down all the left and right coset. 韩星不知道要做吗？不知道。把 G 里面的东西，全部 G 里面的东西乘一乘这个 group， 看你得到什么东西。G 里面有什么 ？S3 里面有几个东西？6个东西吧，全部 try 一 try， 看下发生什么事情。我先把 S3 的 element list 出来啊。全部 list 出来啊。You must do this experiment. This is a very important experiment to understand the whole concept.
Look at the definition of coset. You take one element in G, you multiply every element in your H. Okay, so there are 6 choices you have. That's 3. Yeah, do it. Left and right. Do all of them. And you will see what happen. Okay. Yeah. So let's check together. So if you take identity multiply X, what do you get? You get back your original group. And you should supposed to get another choice, right? That has the same element as H, which is what? 1, 2. So if you take 1, 2, multiply into this set here, you'll get the same element, correct or not? 1, 2 multiply E, you get 1, 2. 1, 2 multiply 1, 2, you get E. So you kind of permute things inside. What else? 1, 2, 3 H, what do you get? What's the coset you get? 1, 2, 3 times E, and 1, 2, 3 times 1, 2, what do you get? 1, 1 什么? 3. Okay. 1, 3. So can you see that this coset is not a subgroup because there's no identity inside there already? Okay. But at the same time, this is equal to what? 1, 3 times H also. Okay. One more. If you take 1, 3, 2 times H, what do you get? 1, 3, 2 and what? 等一下。1, 3, 2 and what? Sorry? So you take 1, 3, 2 times 1, 2, what do you get? 这两个乘起来得到什么？还记得怎么算吗？ 1, 3, 2, 3和 1, 2怎么算呢？ What do you get? 2, 3. Yeah, 2, 3. So actually, if you compute, actually 2, 3 times H also get the same set here. So what can you see here? Why these two get the same set? Actually, what did you observe here? Actually, they are just different representatives inside your set. Okay, actually, they are just different representatives inside. Okay, no? Okay. So how many coset here in this case? How many coset? How many left coset here? How many in total? 1, 2, and 3. Okay, so there are only 3 cosets. But how many elements of H inside here? Which is 2. But we got a formula, right? The order of S3 is equal to what? The order of a subgroup times the index of the subgroup. In this case here is what? 2 times 3, which is 6. Agree or not? We know that 3 factorial
is the order of H3. Okay, so they agree. Okay. How about the other case? How about the other case? If we do left coset, so yeah, agree, good. How about on the other hand? Okay, so what are these right coset here? So let's list down what are these right coset. So H is equals to E and 1, 2. Okay, similarly, this is equal to H time 1, 2. But what is H time 1, 2, 3, for example? You should get 1, 2, 3 and 2, 2, 3. Okay, and then this is H time 2, 3 as well. Okay, you pick this different representative. If you don't believe, you go and compute also. Okay. So again, you will get 3 right coset also. Okay. Again, you have a similar theory for right coset. Okay, if you define the index as a right coset, okay, you have a similar theory here. But note that here, what can you observe here? What is 1, 2, 3 H and H1, 2, 3? Okay, seems like if you change the order of multiplication, you get different coset. Okay, you partition differently. Okay, you partition differently. Can you notice? So here got 1, 2, 3. Here got 1, 3, but here 1, 2, 3. Here 2, 3. So it's different. In general, left and right coset don't agree. Okay, in general, they don't agree. So verify that 1, 2, 3 H is not H 1, 2, 3. Okay, but the number of left and right coset agree. Okay, but the number of left and right coset agree. But the number of left coset. But the number of left coset and right coset will agree. Okay. So usually you can do the theory using left coset or right coset. You can go through the whole theory again. Okay, what we did before. You can prove it. So left and right somehow, okay. I mean, give the same number. They give the same number, but they cut differently. Okay, they cut the your group cake differently. So generally, right coset are not left coset. Although they have the same number 数目是一样的，但是它们长得不一样。OK 了吗？ Yeah， 数目是一样的，但是它们长得不一样。But, however, if we have a more condition on my subgroup, which is normal, okay? If my subgroup is normal, then the right coset will be equals to the left coset. We will show it later. Can you recall what's the normal definition of that? Gn G inverse equals to n. Does it give you Gn equals to Ng? Okay, so we commute with G. All right. So I put another remark about the number here. So the number of left coset, okay, in general, I mean, not in general, it's always, okay, it's always the same as the number of right coset. It's always the same. How to prove it? Okay, you should prove that. Prove what? If HA equals to HB, if and only if AH equals to BH. You can prove this. Actually, this proof comes from the TFAE statement. You can do generalization from that. Remember that yesterday I told you you can sort the order inside your TFAE. Once you sort the order, you can prove a statement for HA equals to HB. And then there will be equivalent there. Okay, try think about it. Okay, try think about how to extend
the proof of TFAE to prove this statement. Okay. Fine. And then the hint I'll give you is try to swap the order. For example, we prove that x inverse y is in K. You can swap the order, right? Y of x inverse y times x inverse of K. Y times the inverse of x is in K also. And then y inverse x is in K also. And then x times y inverse is also in K. Then you can do this right coset statement here. Okay, try. Okay. Any questions so far? Okay, so let's continue. Two more propositions to go, and then we can discuss the assignment. Again, so we will prove this left-right thingy for normal subgroup. So let's prove another TFAE statement here. Okay, for normal subgroup. So first, hash is normal. So what does it mean by hash is normal here? Means that for every hash in H, for every G in G, the conjugation of H should live in the subgroup. Second, I think we have proof 1 to 2 here. So second is for every G in G, GH, G inverse is equals to H. I will prove this equivalence, I think. We prove one way, and then the other way is obvious. That's what I said last time. But how about the third one? GH equals to HG. I think it's also obvious. Is it obvious? 2 implies 3, 3 implies H. Once you have 2, you can write GH1 G inverse equals to sum H2. And then you move the G across. And then you can write GH1 equals to H2G. And then you show the other inclusion. Okay. And then I think the non-obvious one is the last one, which I mentioned just now. Left coset of H in G is a right coset. Okay. So how about going from 3 to 4 and 4 to 3? Okay, so 1, 2, 3 I left for example, left for exercise. We have discussed before. But how about 3 to 4, 4 to 3? Well, I guess one direction is obvious. Which direction is obvious? Which direction is obvious? 3 to 4 or 4 to 3? 3 to 4, right? Because we already know that GH is already equals to HG for all G. So every left coset must be equal to the right coset. But how about the other way? To show the other way, what do you need to show? You need to show a set equality here. Okay, so you need to show two inclusion. Right, so let's do only 4 to 3. Okay, so how do we start? So suppose AH equals to HB for some AB in J. Okay. What do you want to show? We want to show that actually A equals to B. So this is what we're going to show. See, 3和4的差别是什么? The difference between 3 and 4 is what? 4 is very general, you know. It just says that every left coset is a right coset. It can be HB, where B is not A. It can be A also. All cases can be considered. But the statement here is strong. If H is normal, this B cannot simply pick one. Must be A. Okay, 4 is a more general statement than 3. Okay? 4 is more general. Right. So when H is normal, we only have A equal to B. So let's see how are we gonna do. Let's think a bit. What to do? So this trick is quite important in this course here. The proof of this statement. So how are we gonna show it? 那你们想得到吗?
Okay, maybe you need to think about partition here. Okay, so these coset are partition group. So there's only one property you need to remember for your coset. It partition the group. Okay, and then this partition is actually very strong. Like what I told you, right? For example, identity only can live in one of the coset only. So it is quite strong. You know where exactly people at. You cannot stare at two places at once. Where you can only stare at one place. So, what's the important element here to see? So you can note that A is also in HB. Right. Why? Because we know that HB equals to AH. And what? And what? Why? A is in AH, right? Since what? Since A is equals to A times the identity. Okay, let's put it 1 here. But at the same time, obviously you can put 1 times A, but I'm not sure it's important. Let's write it here first. Okay. So what can we argue here? I think 1 times A not important. Just like this. A live in HB. So a question is, how about, so a side question is, how about A, HA? Is A in HA or not? Huh? A is in HA or not? No question. I mean, no idea. HA contains what? H contains what? H is a subgroup, right? It must contain identity. So E times A is what? A, no? So A also live in HA. But you think 想一下你有一个 HB. Okay, let's think a bit. HB, you got A. HA, you also got A. But what did we say? This right coset will partition your set. If they have non-trivial intersection, meaning what? They have to be the. Yes, this is a general theory for partition. If the two partition has non-trivial intersection, they must be the same. Okay. So by general theory for partition, make sure this is in the chapter 0. Chapter 0, make sure this one is in the partition and the equivalence relation. So by general theory for partition, since HA intersect HB is non-empty, okay, then HA must be equal to HB. Okay. Any question? Any question? 问题，来问题，来问问题，我们就要去最后一个了。Want to show 在哪里？啊？哦，我在做梦啊！我傻了我，我发什么神经？我在做梦哈！哦，喂，我在做梦，我在做梦。我在做梦啊！我想一下，我正了这个，我加 induce 那个，我想一下。啊？什么？我是不是做错东西了？什么？说说看。 我在干嘛啊？Wait, let me think。有东西做错没？啊，对啊，没有东西做错啊。I mean，啊，because 对吗？对吗？因为我证到 HB 等于 HA 嘛，then AH by definition by assumption AH 等于 HB，and then 我们证到 HB 等于 HA。Want to show 为什么写错嘞？Right, exactly, right。可能我们会选不一样的 representative 啊。对，我们可能会选不一样的 representative。对，I mean, okay, good，可以。Right. So the problem here is 我们不一定要选到同一个 representative，还记得吗？因为有时候我们可以证到它是一，比如说 for example，给一个 example，在 let's say Z6里面 ，maybe 你的 AH 是 let's say 5，OK，maybe 你可以证到它是11，或者你也可以证到它是16，something like that，不一定要整整。Maybe you can prove that this right coset is 11 or 16, but they are all 5. Okay, you don't need to pick the same representative. That's what I mean. Yeah. Okay or not? Any question? Yeah, so the main point is to show that you get the same coset. Yeah, maybe you can pick a different representative. Yeah, you are right. Yeah. But I mean, once you get back to the same coset, then what? Then you can pick back your representative A. It's okay. It's fine. Okay. But the main point here is Eric wants to say that as long as we show that they are the same cosize. If you pick different representative, it's also fine. Okay. Question? 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 Any question? Other question? No? Okay. So let's do the last one. Please ask 不要扭捏捏啊，我们要直一点。Okay. So next, let's say we have a subgroup H, and then we take any G in G, then what? Then you can consider this conjugate subgroup here. Okay, we claim that this is a subgroup again. Okay, this is for any G. Okay, everyone read the notation here. If you have a subgroup, you conjugate this whole subgroup here. It's again a subgroup. Hey, actually, you learn this diagonalization of matrix. If you take PDP inverse multiply PD 2P inverse, PDP inverse again, then you will get again diagonal matrix with a conjugation again. They will cancel out when you multiply. Okay, so the other statement is if a group G has just one subgroup of order R, then that subgroup is normal. Okay. So you might wonder what R is this? A random R is fine. But the problem is here is this random R you only has one subgroup of it. Then this group have to be normal. 会很奇怪吗这句话？你有一个 size R 的 group， 但是问题是你在这个 group 除了它就有它吧？不是没有其他 subgroup 啊，是没有其他 order R 的 subgroup. There's no other order R subgroup. Then this subgroup has to be 很奇怪哦，不奇怪，不奇怪，你要告诉我一下，因为我不知道为什么。 有点奇怪 at least for me. Okay, so we need to prove it. Okay, let's prove it. So let's prove the first one first. I think first one is very quick. So to check subgroup, what do we need to check? Closure, and then identity, and then inverse. How is it closed? So we just quickly check closure. So what is G, for example? G. So we need to fix a G first, by the way. Correct or not? We fix a G first, and then we look at different H. So let's say, what is G H1 G inverse times G H2 G inverse? What is this? Like quickly. Email. G HE H G inverse. Does this live in G H G inverse again or not? Why? Because H is a subgroup. Okay, close under take in multiplication. How about identity then? Can you cook out an identity or not inside this group? Inside GH G inverse. Can you cook out the identity? How to cook it out? So can you write it in the form of G of some H times G inverse or not? Sorry? G of what? G of E? Because subgroup contain identity. Okay. And then lastly, inverse. Let's say I have a G H G inverse. So what's the inverse of this guy? What's the inverse of this guy? What do you think? So inverted, right? Invert and then taking inverse. So what do you get? Again, G inverse, H inverse, G. How to check this? You need to check, right? Definition of inverse is what? Left multiply, right multiply, you get identity. So you quickly check. Is it you left multiply, right multiply, you get identity. Okay, I hope you do. So again, this guy live in GH, G inverse. Why? Because H is a subgroup, and then inverse of H as is. So you can see all the property that we have used here is using H is again a subgroup. Okay, first one, Y close because H is closed also. Second, Y has identity because H got identity. Third, why you have inverse because H got inverse also. So we really just using the property of H. Okay. Right. How about the last one? Okay, last one. Okay. Okay. How about last one? So last one is a bit important, quite important. And by the way, there's a second proof for this statement here. I think we're not going to show now. Maybe I show it next class. I don't want to add more things to that. So let's do B first. So let's start with what is given. Sorry. So suppose hash is a subgroup of order R. Oh, I think we need that proof there. This proof needed. So the claim is, let me claim for you first. GH inverse is also a subgroup of order R. Okay, let's stare at this claim first. Is it obvious or not? If your subgroup has order R, then if you conjugate it, the size is still R. Is it obvious? Think about it first. I'll prove it to you. Think about it. Is it obvious or not? 比如说你的 subgroup 有3个东西，为什么你随便 conjugate 把一个东西过后，这3个东西还是不一样的？它不会变少，对吗？最多它会变少嘛，不可能变多了嘛。你不能从3个东西变出4个东西，它可能变少 ，maybe reduce because they might be equal after conjugate. But turns out that it won't. Okay, turns out that it remains. Okay, 想得到为什么吗 ？Okay, 想不到的话 ，we need to prove a lemma. So we need to prove a lemma. So lemma is there's a map called phi g from G to G. What do? I send X to GX, G inverse is N. Okay, I introduce a new term here, automorphism. Okay, so let me tell you what's automorphism here. So automorphism here means you have a bijection to yourself. 你自己. Okay, bijection to yourself. Automorphism. Now let me put here. Bijective homomorphism onto itself. Okay, 自己去自己的 isomorphism, 我们叫 automorphism. Okay, the isomorphism that happen between itself. Okay. Homo 容易检查吗 ？Homo 容易检查吗 ？Homo 容不容易检查？放在脑里面检查一下。脑里面要放什么东西 ？VGXY. Okay, let's check this. What is VGXY here? Is GXY G inverse. But remember, what's our goal here? We want to write it as VGX times VGY. But what is VGX times VGY? By definition, it is GX G inverse, GY G inverse. So you just created a identity in between all. Okay. So homo is okay. How about injective and surjective? Okay. Prove injective for what? For a homomorphism, what do you need to know? There's a very useful statement, right? The kernel have to be identity. Okay, so you ask yourself, when is GSG inverse is identity? This is only true when? This is only true when X is equals to identity. Use what? Cancellation law. Okay. So if and only if, because your kernel have to be equal to identity. Okay, only contain identity. Surjective? Surjective is what? So who gets sense to Y for all Y in G? Think about it. 什么东西要塞在 G 和 G inverse 的中间，你才会拿到 Y。G inverse Y G. But the problem here is whether this guy live in G or not. Live 吗 ？live 不 live 在 G？ live 吗？为什么 ？G inverse exists in G, and then G is closed under taking. Sorry, what am I saying? Closed under taking multiplication. Okay, so what? We have a bijection between these two groups, right? So meaning these two sets has the same element now. Okay, 有 bijection between two sets, 它们就有同样的数量。Okay, once we have a bijection, they have the same order. But question says what? There's only one subgroup of order R. But now we found two subgroup of order R. Meaning what? These two have to be the same. So since there's only one subgroup of order R, these two have to be the same. But what do we say about if a subgroup satisfies GH G inverse equals to H? We say that actually almost by definition or the previous proposition, we know that H is actually normal. Okay. Yeah, so we rely on the fact that we have a bijection between GH G inverse and H. Okay. Right. Any question? Any question? No? Okay. Hey, you guys are willing to stay for another 15 minutes or not? Or you guys have event? Dinner, your meeting, Okay, then we postpone to next. I booked the room already. So next Monday, we have a replacement. in the morning. Yeah, morning. 早上 bro. Yeah, 早上. Sorry? Tuesday morning we decide on Tuesday night. Tuesday so next week. No 啦，没有吧？我嘴巴讲咩？可是我日期是写29。该讲吗？哦，对，讲错。Tuesday. So next Thursday is a holiday. So Tuesday morning replacement, Tuesday night we got a class, and then we have 2 classes for next week. Okay, and then next Friday is the due date for your assignment. Okay. Okay, so we'll discuss assignment next week.